Okay, Assalamualaikum dan salam sejahtera. Okay, for lesson 12, chapter 8, we cover 8.1, 8.2 and 8.3. Topic is physical optics, which is the study of the wave nature of light. Okay, we focus on interference and diffraction phenomenon. Okay, chapter 8 for physical optics, allocation hour is 2 hours. We have 6 subtopics. 8.1 Heightened Principle, 8.2 Constructive Interference and Destructive Interference, 8.3 Interference of the transmitted light through the double slit, 8.4 Interference of the reflected light in thin film, 8.5 Diffraction by a single slit, 8.6 Diffraction grating. Okay, for lesson 12 we cover only 8.1 until 8.3 interference of the transmitted light through the double slit. Okay, 8.1 Heightened Principle. Okay, learning outcome for 8.1 Heightened Principle. We focus on spherical and plane wavefront. For B, sketch and explain the wavefront on of light after passing through a single slit and obstacle using Heightened Principle. Okay, Heightened Principle state that every point on a wavefront is the source of wavelets that spread out in forward direction at the same speed as the wave itself. The new wavefront is a line tangent to all the wavelets. Okay, look at A, plane wavefront, and this is our plane wavefront. Okay, let's say I have 3 point source. Okay, the first point source is a source of the new wavelet. The direction is in the forwarded direction. So second point on the wavefront is the source of the new wavelet. The third point is the source of the third wavelet. Okay, so tangent of all the new wavelet, if we combine, so we get the new wavefront, second wavefront. Okay, for B we have spherical wavefront. So this is our spherical wavefront. Every point on this wavefront is a source for the new wavelet. Second point is a source of the second wavelet. Okay, third point is the source for the new wavelet. Okay, tangent for this wavelet is after we join, so we get the new wavefront. Okay, next. Okay, wavefront. Okay, what is wavefront? Okay, wavefront is a line or surface which join all the adjacent points which have the same phase and amplitude in a wave. The direction of propagation of a wave is perpendicular to the wavefront. And let's say I have a spherical wavefront, so source 1. Okay, the direction of the wave is in all the direction. Okay, so the wavefront is a line or surface and we join all the adjacent point. And let's say just now we have discussed, okay, for this wavefront, every point on this wavefront is a source of the new wavelet. So after we join all the adjacent point, we have the same phase and amplitude in a wave, and the direction of wave propagation is perpendicular to the wavefront. Okay, so the distance between this wavefront and the second wavefront we call wavelength. Okay, next, how to sketch the wavefront. Okay, first we draw a plane or spherical wavefront. Okay, point 2. Okay, choose a few points on the wavefront, at least 3 points. Okay, let's say this plane wavefront, and we choose 3 points, point 1, point 2, point 3. Okay, step 3. Draw the wavelet for each point. Okay, source 1. Okay, this is a source for the new wavelet. Source 2. Sketch new wavelet. Source 3. Next, sketch new wavelet. So the the tangent line, we can build the new wavefront. Okay, step 4, join all the tangent line of the wavelet to build the new wavefront after several times. And so this is the result of the wavefront. Okay, so this is our plane wavefront, and we also have the circular wavefront. The direction of the wave propagation is forwarded. Okay, next, and we have the wave. Okay, how to sketch wavefront, okay, of a light after passing through a single slit, and this is called single slit, and obstacle. So this is the example for obstacle. Okay, what we can see after a wave passing through an obstacle, the end of the wave is bent. Okay, explanation. According to the Heightened Principle, every point on a wavefront can behave as a secondary source of light which can propagate out light wave with the speed of light. Okay. Figure above show a new wavefront which is constructed by the drawing a line tangent to all the wavelet from the secondary source of the old wavefront. After drawing several wavefronts, the wave is seen to bend around, and the wave is seen to bend around. And look at this. Okay, and the wave is seen to bend around the edge of the single slit or obstacle, and like this also. After the wave passing an obstacle, and the wave seen to bend around. Okay, the bending of wave is called the diffraction. And the degree of bending more extremely for small opening, and the degree of bending is more extreme for a small bending. And compare this the bigger one and the smaller one. So if the D is very small, so it seems more extreme for small opening. Okay, now we proceed with 8.2, constructive interference and destructive interference. A, define coherent. B, state the condition for the interference of light. Sorry, typo here. C, state the condition of the constructive interference and destructive interference. Okay, remarks. We emphasize on the path difference and its equivalent to the phase difference. Okay, what is coherent source? Coherent source are those which emit light wave of the same wavelength or frequency, which are always in phase with each other, or have the same or have a constant phase difference. Okay, remember, coherent source are those emit light with the same wavelength or frequency, which are always in phase with each other or have a constant phase difference. Okay, look at this slide. Okay, I have laser light. Okay, passing passing screen with one slit. Okay, next we put screen with the two slit. So our laser light, okay, pass through single slit. Next, pass through two slit. Okay, so this is the way how to produce two coherent source. Remember, what is coherent source? Okay, same frequency or wavelength. The source are in phase. Okay, look at the beginning. Same phase, which is crest. The second source also start with crest. Okay, so in phase and constant phase difference. Okay, why we don't use white light source? Because white light source have different frequency. Red light, green light, the blue light, and so which is not constant in frequency. How about monochromatic light of the light source? Okay, so what you can see, the ray is diverge. Okay, compared to when we use the laser light. Okay, when we use the laser light, the ray is more directional. Okay, so constant phase difference, okay, same frequency and in phase, and that's why we use laser light source. Okay, next. Okay, next slide. Okay, two types of coherent source. Okay, two types of coherent source. A, in-phase coherent source. Okay, in-phase coherent source. Okay, look at S1 and S2. Both S1 and S2 start with the crest. Okay, start with the crest. Okay, or if both S1 and S2 start with the true, also we call in-phase coherent source. Okay, how about anti-phase coherent source? Okay, look at this. S1 start with the true, S2 start with the crest. Okay, so this for this situation we call anti-phase coherent source. Next, okay, interference of light wave. Okay, when the two coherent light meet in a region, they undergo superposition and the result in constructive and destructive interference. According to the principle of superposition, when the two or more waves overlap, the resultant displacement at any instant of superposition is equal to the vector sum of the individual displacement of the wave. Okay, next slide. Okay, path difference. Okay, what is the path difference? Path difference is the distance. Path difference is the difference in the distance. The difference in the distance in terms of lambda, and which is traveled by the two waves from their respective source to the same point in a region. So this is our region. Okay, source 1, source 2. Okay, source. This is the light path 1 and this is light path 2. Okay, so we draw a tangent line and we draw a line perpendicular to the light path 2. So we get this path difference. Okay, the path difference is in terms of lambda. SI unit is meter. Okay, so we can use it is used also to determine the phase difference, but phase difference in terms of pi. Okay, unit radian. Okay, which is the between the two light ray when they meet at a point. Okay, so the path difference, if we call path difference, is the difference in distance in unit lambda. Okay, if we use phase difference, okay, if we calculate phase difference, it is determined in terms of pi. Okay. Next, okay, we have constructive interference. Okay, what is constructive interference? It is occur when the crest of one of wave fall on the crest on another, such that the amplitude is maximum. Okay, reinforcement of amplitude that will produce a bright fringe, or we call maximum. Okay, under constructive interference, we have in phase source. Okay, look at this slide. Look at this diagram. Source 1 and source 2. Okay, you focus on the beginning. So this is the in phase source. Okay, the shape is same. That's why we call in phase source. What happened to the end? Okay, also same in shape. Okay, so at the end, at point O, appear the bright fringe. Okay, so the reinforcement of amplitude. Okay, the amplitude is maximum. Okay, so for constructive interference for in-phase source, it occurs if and only if the path difference between the wave has to be any whole number of the wavelength. Okay, now let us count together how to calculate this path difference for this case. Okay, for source 1 we have 1 lambda, 2 lambda, 3 lambda. For source 2 we have 1 lambda, 2 lambda, 3 lambda. Next, calculate path difference. Source 1 minus source 2. 3 lambda minus 3 lambda, we get 0. Okay, so we can summarize. So path difference for the constructive interference in phase source, we can use formula path difference equals to m lambda, where order, and m equals to 0, 1, 2, 3. Okay, so when we substitute order 0, so path difference 0. When we substitute order 1, okay, m substitute 1, so we get lambda. Okay, so if we substitute 3, so our path difference is equals to 3 lambda. Okay, next, we also can calculate phase difference. Phase difference is in terms of pi, path difference in terms of lambda. Okay, so phase difference delta P equals to m times 2 pi. This formula only applicable for constructive interference in phase source. Okay, if order equals to 0, so our phase difference is 0. If order equals to 1, and we substitute 1 here, so we get answer 2 pi. If order equals to 2, we get answer 4 pi. Okay, next, okay, so this is the two types of interference. Okay, the first one, we start with constructive interference. Okay, next, we go for the constructive interference. Oh, before that, okay, look at this slide. Okay, the example for the constructive interference in phase source. Okay, source 1, okay, determine the length of the wavelength. Determine the length of the wave for source 1. Okay, we have 1 lambda, 2 lambda, and quarter. Sorry. Okay, 1 lambda, 2 lambda, and quarter. For the source 2, 1 lambda, 2 lambda, okay, 3 lambda, and quarter. Okay, so determine the path difference for this shape. Okay, source 1 minus source 2, or here source 2 minus source 1, 3 and quarter lambda minus 2 and quarter lambda. So the answer is lambda. Okay, the answer is lambda. Okay, so here we have here to show the reinforcement of amplitude. Source 1, okay, plus source 2. So what happened to the amplitude? And become bigger. Okay, next. Okay. Next, we go for the constructive interference antiphase source. Okay, why we call antiphase source? Okay, look at the beginning. Source 1, okay, here is through meet the crest. So here we call antiphase source. Okay, at the end, what happened? Okay, through meet the true. So here, appear the bright fringe because the reinforcement of amplitude. It occurs if and only if the path difference between the wave is an odd multiple of lambda over 2 wavelength. Okay, let us come together how to determine the path difference. For the source 1, 1 lambda, 2 lambda, 3 lambda, and half lambda. Okay, so we have 3 and half lambda. Next, for source 2, we have 1 lambda, 2 lambda, 3 lambda, 4 lambda. Okay, so 3 and half lambda minus 4 lambda, we get answer half lambda. Okay, so formula for the path difference for constructive interference antiphase source. Okay, we have formula m plus half lambda, where order start with 1, 2, 3. Okay, if order equals to 1, answer path difference equals to lambda over 2. If order equals to 2, and answer we have path difference 3 over 2 lambda. Okay, next for the phase difference, and which is in terms of pi, and formula we use delta phi equals to m plus half lambda. Okay, m plus half times 2 pi. If our order is 0, we substitute 0 here, so our answer is pi. If our answer order 1, and we substitute order 1, okay, 1 plus half times 2 pi, so we get answer 3 pi. Okay, for this example, refer to the source 1, start with the true, source 2 start with the crest, so we call antiphase. Okay, so the ending, so look at this shape. So we can see after we add source 1 and source 2, we can see the reinforcement of amplitude. So this will produce a constructive interference. Calculate the path difference. For source 1 and for source 2, we calculate 1 lambda, 2 lambda, 3 lambda, 4 lambda and half lambda, 4 and half lambda. For source 2, 1 lambda, 2 lambda, 3 lambda. So source 2 minus source 1. So the difference is, in path difference is lambda over 2. Okay, next we go to the destructive interference. Okay, destructive interference, it occurs when the crest one of the wave fall on the true of the other wave, and another wave that such the amplitude is minimum, which is cancel each other. The total cancellation of amplitude that will produce a dark fringe. So at point O here, we produce a dark fringe or minimum. Okay, we start with destructive interference, antiphase source. Why we call antiphase? Okay, look at the beginning. Source 1, okay, like this shape. Source 2, okay, so here we have, okay, crest. Source 1 we have true. So source 1 and source 2 are antiphase. Okay, are antiphase. Ending. Okay, ending. Okay, what happened after source 1 and source 2 overlap each other? So at the end is a total cancellation of amplitude and produce the dark fringe. Okay, so destructive interference antiphase source, it occur if and only if the path difference between the wave has to be any whole number of the wave. Okay, let us come together. For the path difference, source 1, 1 lambda, 2 lambda, 3 lambda. For source 2, 1 lambda, 2 lambda, 3 lambda. So 3 lambda minus 3 lambda is equals to 0. Formula path difference for the destructive interference antiphase source, okay, equals to m lambda, where the order we start with 0, 1, 2, 3 and etc. Okay, so if m equals to 0 and we substitute, we put 0 here, so our path difference becomes 0. If our order start with 1, okay, so m substitute 1, so our answer is equals to lambda. Okay, in terms of phase difference, which is in terms of pi, okay, so delta phi equals to m lambda. If order start with 0, our answer is 0. If our order start m equals to 1, our answer is 2 pi, and so on. Right. Next, we have destructive interference in phase source. Why in phase? Okay, look at the beginning. The shape is same. Okay. Why destructive? Look at the end. Okay. So source 1 overlap with source 2. So it will cancel each other. So appear at point O is the dark fringe. It is occur if and only if the path difference between the wave is an odd multiple of lambda over 2 wavelength. Okay, for source 1, okay, let us come together. Lambda, 2 lambda, 3 lambda, 4 lambda. Okay, for this wave, 1 lambda, 2 lambda, 3 lambda and half lambda. Okay, so source 1 minus source 2, we get lambda over 2. Formula path difference for the destructive interference in phase source, okay, m plus half lambda. If order m equals to 1, our path difference is lambda over 2. If order m equals to 2, our path difference, and we substitute 2 here, so we can answer 3 over 2 lambda. Okay, for the phase difference, okay, for the phase difference in terms of pi, okay, so delta phi equals to m plus half times 2 pi. If our order start with 0, so we put 0 here, so our answer is pi. So our phase difference is pi for the order m equals to 0. Okay, so if our order m equals to 1, our answer is 3 pi, and so on. Okay, next, and this is the condition to produce the interference. Okay, so we have 3 conditions. The first one, to produce the interference, Okay, we need a coherent source which is constant phase difference and the same wavelength. Okay, same amplitude. The slit is small enough that it can be considered a point source of light. Next, the condition to produce the constructive interference. We have 4 conditions here. The first one, coherent source, constant phase difference and the same wavelength. Now, point number 2, same amplitude. Point number 3, the slit is small enough that it can be considered a point source of light. Okay, point number 4, in phase source. Okay, next, condition to produce the destructive interference. And we have 4 conditions here. The first one, coherent source, constant phase difference and the same wavelength. Okay, second point, same amplitude. Third point, the slit is small enough that it can be considered a point source of light. And the last one, to produce the destructive interference, we should have the antiphase source. Okay, so this is the summary. Okay, the condition for the path difference of constructive interference and the destructive interference for in-phase and antiphase source. So how to read this table? Okay, for the first column, we have 2 coherent source, in-phase and antiphase. Okay, for in-phase, we have 2 types of interference, constructive interference and destructive interference. Okay, let's read together. In-phase, coherent source, constructive, so the path difference, m lambda. Okay, for in-phase, destructive, and for in-phase source, destructive interference, so formula m plus half lambda. Okay, for antiphase, antiphase source, destructive interference. Okay, so we use m lambda. For antiphase source, constructive interference, so we use m plus half lambda. Okay. Next, we go to the 8.3, interference interference of the transmitted light through the double slit. Okay, we have 2 learning outcome here. A, derive and use Ym equals to m lambda capital D over small d for the bright fringe, or we call maxima. Point number 2, Ym equals to m plus half lambda capital D over small d for the dark fringe minima, where order start with 0, 1, 2, 3 and etc. Okay, for B, okay, delta Y equals to lambda capital D over small d, and explain the effect of changing any variable. Okay, so this is the schematic diagram for the Young double slit experiment. Okay, so next we go to the next slide. Okay, this is the schematic diagram for the Young double slit experiment. So for B and C, what we can observe with our eyes. Okay, so here we have a ray passing through slit 1 and slit 2, source 1 overlapping or interfere with source 2. Okay, so di sini, okay, so on the screen, viewing, we can see the fringe is alternate each other, bright dark, and bright dark je lah. Okay, next, okay, we go to the explanation, how to explanation about Young double slit experiment by using Heightened Principle. Okay, Young double slit experiment is one of the experiment that show us the result of interference phenomenon. Okay, the monochromatic wave of the wavelength lambda is entering the slit S1 and S2, which are at the distance d apart, and the distance between slit 1 and slit 2. Okay, after passing the slit, the wave spread out in all directions using Heightened Principle. Since these two waves emerge from the same source, they could be considered coming from the two coherent source. Remember what is coherent source? Same frequency, same wavelength, in phase and constant phase difference. Okay, the light wave from these two waves would interfere. What is interfere? Overlapping. Okay, the interference pattern was then projected onto a screen, and we can see the pattern of alternating bright and dark fringe. Okay, next. Okay, so this is the schematic diagram for the young double slit experiment. Okay, interference pattern. Okay, what we can see, it start with m equals to 0. We call the central bright fringe. Okay, but we can see okay, a monochromatic light passing two slit S1 and S2. Okay, so the ray will overlapping each other. Source 1 overlapping with source 2. So it will produce the constructive interference. We start with the central bright fringe, order m equals to 0. Next, alternate with the dark fringe, m equals to 0 for the first dark fringe. Okay, right. For what is the bright fringe? Bright fringe is the interference is constructive. Intensity is maximum here. Okay, for the dark fringe, interference is destructive. Destructive, the intensity is minimum. Okay, so here, okay, look at this diagram. Consider young double slit schematic diagram as shown in the figure above. Let point P will be the point on the screen, where the point source 1 and source 2, okay, interfere, overlapping, and here produce the bright fringe. Okay, point P will be a point on the screen. Okay, capital D. What is capital D? Capital D is the distance between the screen and capital D is the distance between the slit, this is our slit, and the screen. So this is our capital D, the distance between slit and screen. Okay, small d, separation distance between slit 1 and slit 2. Slit 1 and slit 2, so this is the small d, and separation between the slit. Ym, y subscript m, is the distance from the central maximum to the m order fringe, either bright or dark fringe. Okay, here, okay, the dot. Okay, so this is our central bright fringe. Okay, ym is the distance between the distance from the central bright fringe to the order we want to calculate. Okay, let's say here, okay, central bright fringe, first bright fringe, second bright fringe. So I want to calculate the distance between the central bright fringe to the third bright fringe. So I need to consider from the central bright. So ym is the distance from the central maximum to the order that we want to calculate. Okay, now look at this slide. Okay, derivation of the double slit equation. Okay, tangent theta. Tangent theta is ym over d. Okay, ym, the distance between the central bright to the order that we want to calculate. Okay, the distance here. Okay, and d is the distance between slit and screen. Okay, slit and screen. Okay, so here theta is here. Okay, you draw a line as hypotenuse. So theta here. So d is our opposite. Sorry, d is our adjacent. Ym is our opposite. So opposite over adjacent is tangent. Okay. Okay, now I refer to the source 1, the light ray for the source 1. Okay, and then light path for the source 2. The difference between source 1 and the source 2, here we have path difference. Okay, our path difference here equals to d sin theta. Why d sin theta? Okay, from source 1, source 2, we have small d, the distance between two slits. We draw a line from source 1 to source 2. Okay, so right angle here. So can you see theta here? Okay, so this is our hypotenuse. Okay, and d sin theta here, our path difference is opposite. How to calculate our opposite? So we use sin theta. So D, so to calculate path difference, equals to here D sin theta. Okay, because the angle is very small, we can approximate the sin theta to tangent theta. So tangent theta opposite over adjacent, ym over d equals to tangent theta. Because the angle is very small, we can substitute tangent theta with sin theta. So we have sin theta equals to ym over d. Okay. Okay, so consider both constructive and destructive interference are in phase interference. Okay, for constructive interference, okay, or sometimes we call bright fringe or maximum. Okay, for the path difference, and refer to previous slide, we have delta L equals to d sin theta. Okay, from 8.2, we have path difference equals to delta L equals to m lambda. So by comparing the first equation and second, okay, so we have equation d sin theta equals to m lambda. Okay, we know that sin theta is equals to ym over capital D. Okay, by rearrange the equation ym as a subject matter, so you have equation ym equals to m lambda capital D over small d. Okay, next we go for the destructive interference. Okay, the dark fringe, or sometimes we call dark fringe or minimum. Okay, from the previous slide, and we know that the path difference is delta L equals to d sin theta. Okay, and also we have delta L equals to m plus half lambda. By comparing equation 1 and equation 2, and we have d sin theta equals to m plus half lambda. Okay, ym as a subject matter, now your equation become bracket m plus half lambda capital D over small d. What is ym? Ym is the distance of the fringe from the central maximum. M is order number. Okay, 1, 2, 3. Okay, lambda is the wavelength of the light source. Capital D, small d, the distance between the both slit. Okay, capital D, the distance between slit and the screen. Okay, right, for this slide, okay, this is the order number in the double slit interference. Okay, how to determine the order number. Okay, the first one we have constructive interference formula. Okay, ym equals to m lambda capital D over small d. Okay, for the young double slit, we start with the central bright fringe. Okay, in terms of bright order, it is 0 order. Okay, for order number, we use m equals to 0. Okay, next we go to the first bright fringe. Okay, for the bright order, we call first bright order. And order number, we use m equals to 1. Okay, for the second bright fringe, okay, in terms of bright order, we call the second bright order. Order number m equals to 2. Okay, next, we go for the dark fringe, okay, or destructive interference. Okay, formula we use ym equals to bracket m plus half lambda capital D over small d. Okay, for the dark fringe, okay, for the dark fringe, first dark fringe, okay, in dark order, we call 0 dark order. Okay, for order number, we use m equals to 0. For the second bright fringe, and we call the first dark order. Okay, so we substitute m equals to 1. Why minus y second dark fringe and order number m equals to 1? Because the for the young double slit, we start with the central bright fringe. So for the dark fringe, we need to minus 1 to find the order number. Okay, to find the order number for the dark fringe, we need to minus 1. And let's say for the fourth dark fringe, okay, order number 3. 4 minus 1, we get 3. So in terms of dark order, it is third dark order. Okay, look at this diagram. Okay, for at the central, we call the central bright fringe. Okay, so number of order m equals to 0. Next, we have first dark fringe. For order, and we have m equals to 0. Next, we have the first bright fringe. Number of order m equals to 1. Next, we have second dark fringe. Okay, so we use m equals to 1 for order for the second dark fringe. Okay, next we go to the second bright fringe. We use m equals to order for number of order. Okay, for the third dark fringe, okay, we use m equals to 2 for number of order. Okay, next, okay, how to calculate the separation between two consecutive adjacent dark or bright fringe. Between bright to bright, okay, between bright to the next bright, we can calculate delta y, which is the distance between two consecutive adjacent bright fringe or dark fringe. I can calculate the distance between this dark fringe to the next dark fringe. Okay, so delta y. Okay, equation given, delta y equals to lambda, capital D over small d, where lambda is a wavelength, capital D is the distance between slit and screen, small d is separation between the slit. Okay, next, the effect of changing lambda, capital D and small d to the interference pattern. Okay, interference pattern we refer to delta y. Okay, is depend on lambda, capital D and small d. Okay, if the distance between the screen and slit is constant, capital D, okay, and the distance between two slit also constant, okay, what happen? If we use lambda increase, okay, if we increase the lambda, what happen to the delta y? The relationship lambda and delta y is directly proportional. So if we use bigger lambda, the interference pattern become more wider. If we use smaller lambda or we decrease the value of lambda, the interference pattern become more closer. Okay. Next, if lambda and small d is constant, okay, so the capital D and delta y is directly proportional. Okay, if capital D is increased, the distance between screen and slit is increased. Okay, so what happened to the delta y? The interference pattern become more wider. Okay, if we decrease the value of D what happened to the delta y? The delta y is also decreased. So the interference pattern become more closer. If the lambda and capital D is constant, okay, so the yang atas ni constant, so small d and delta y is inversely proportional. So if we increase the distance between two slits, what happened to the interference pattern? The delta y is decreased, the interference pattern become closer. Okay, if we decrease if we increase small d, the interference pattern become more wider. Okay, so if the experiment is carried out in the difference medium, for example the water, the fringe separation delta y is decreased or increased depend on the wavelength of the medium. If the white light is used, the central bright fringe is white and the fringe on either side are coloured. The blue is the colour nearer to the central fringe and the red is farther away as shown in the figure below. Okay, so here is the screenshot of the simulation of the young double slit experiment. Okay, if we constant D and capital D and we change the lambda and we use bigger lambda, lambda and delta y directly proportional. If bigger lambda, the interference pattern become more wider. Okay, if we change small d, we decrease the value of small d, what happened to the delta y? The d decrease, delta y increase. So the interference pattern become more wider. So that's all for lesson 12. Thank you.